So let's get started. So it's a great pleasure to have Professor Adji Bousso Dieng. She's coming from not too far from Princeton, and she actually graduated from Columbia University. So it's a great pleasure to have her back here. She won many awards, including a Google Fellowship, was nominated as one of the rising stars in machine learning by the University of Maryland. She's very active also with Google, has close collaborations with them, also doing a lot of work in terms of social impact on AI and how we can actually basically use that at scale, at the global scale. And so we're very pleased to, and she's leading the Vertex Lab at Princeton, so very happy to hear you about like measuring and enforcing diversity in machine learning. And we've talked a lot about that and issues that related to data sets and biases in data. So very much looking forward to it. Thank you.
Thank you. Thank you, Pierre, for the nice introduction. Welcome, everyone. Thanks for attending the talk. So I lead the lab Vertex at Princeton. The goal is to, I highlighted AI, is for it to be basically a connector between different fields in the natural sciences. After my PhD, I decided that I wanted to leverage AI and develop methods that can actually be useful to some interesting domain in the natural sciences are those domains. So we look at, we have collaborators in chemistry, material science, biology, and I'm hoping that this talk can open up some collaborations with folks in climate. So when, discussing with these domain scientists about problems they run into, one thing that kept coming up one way or another was diversity. And so I started looking at how to effectively measure diversity so that we can enforce it in different areas, in models, in algorithms, and things like that, simulations. And so today I'll walk you through the story about how this work came to be. Basically, one strong motivation for wanting to look at diversity, studying diversity, how to measure it, is that in a lot of things that we do in machine learning, the sciences, we do need to enforce diversity. For example, in generative modeling, if you're building a generative model over some domain, you would want that generative model to not only give you one type of output, but to give you a broad type of output. For example, imagine that you're building a generative model of molecules so that you can run that generative model multiple times to get multiple candidate molecules, and that you want those sets of candidates to be diverse enough that when you go to the lab and test for those candidate molecules and their properties, that you actually can do discovery, that you can find something interesting. If the generative model was only returning one type of molecule with one type of property, that you can see how that won't be very useful. Sometimes you may be interested in another type of task, active search, for example, where you have this very high dimensional space that you want to search over. For example, if people are interested in climate here, let's say you look for catalysts or some solvents that are more prone to sustainability, you would want for this active search to find you a diverse set of those catalysts or those solvents that you're looking for. So diversity comes in there as well. Reinforcement learning, we all know about exploitation, exploration, trade-off. Diversity comes in there as well. Sampling, for example, chemists or a lot of scientists, they run these simulations, molecular simulations. And what happens in that setting is that when you do molecular dynamics, your simulation gets stuck in one configuration. So you can get stuck in that configuration for an extended amount of time, which sometimes you cannot afford. So there's a need to actually accelerate this simulation so that you can explore different basins of your energy landscape. The diversity comes in there as well. You want to be exploring a diverse set of basins instead of just getting stuck in one. If you're doing data subsampling, that's also another area that diversity comes in. You have a broad set of things, a large collection, for example, a large collection of molecules or other items that's in your data that you would look into. So you're a scientist and you cannot afford to run your experiments on all those molecules. You want to just subsample a smaller collection of them so that you can, that's something that's tractable that you can run in the experiment. So there's a need for drawing a diverse set of subsample from a larger collection. Or imagine you're doing Monte Carlo estimation. typically what we do is we just draw randomly from the distribution. We're taking the expectation over and average those to do Monte Carlo. If that distribution is highly multimodal, we want to actually, we cannot draw an infinite number of samples from it to get an accurate estimation. Typically what you do is get a smaller sample from that distribution and do Monte Carlo. We would need that sample to be diverse so that we can have a more accurate estimation. So it's a concept that lurks behind a lot of the things we do in machine learning and in science. And so we'll look into how to measure that. So what would we want out of a diversity metric? That's the first question to ask. What's actually diversity? We would want for it to be interpretable. What that means is that we would like for a diversity metric to be what's called an effective number, meaning that if I have a collection of 5 distinct elements, I want the diversity metric to return 5 so that I can actually interpret these things. We want for it to be maximized when all the samples are dissimilar. So I give you a collection. We want for the diversity metric to be maximized when all the elements in the collection are very different from each other. And we want it to be minimized when all the elements in the collection are the same. Another thing we would want is we would want for it to be reference-free. What I mean by reference-free is that we don't want that diversity metric to need to use an additional probability distribution in order for it to be computed, or another reference data set in order for it to be computed. And in machine learning, we run into a lot of metrics that actually do need this reference in order to be computed, but we want flexibility. So we want our diversity metric to be reference-free, because we are not trying to measure goodness of fit. We don't have a probability distribution like a test set and we're trying to see how we fit it. We're not doing that. We're just interested in evaluating diversity of a collection. So we want also flexibility, meaning we want this metric, just diversity. I give you any collection, I want to be able to give you what the diversity is. So we want for it to be domain agnostic, because that you can use it in many domains without needing to define probability distribution. These are just high-level desiderata of things we would naturally want out of a diversity metric. So the next step of the story was, okay, now that we know what we would want out of diversity at a high level, how do we actually define it? Then we had to look into the field that actually, studies diversity a lot, which is ecology. They study biodiversity and try to see how diverse a population of species is, and that's important for preservation and things like that. In ecology, when you look into the literature, one thing that keeps coming up is that diversity is defined as the effective number of species. This was one of our desiderata, naturally, and it's exponential of entropy. There's a lot of literature sustaining why that is a good thing and why that gives you an interpretation as an effective number of species. And they refer to these things as Hill numbers. Basically, a Hill number will be exponential of entropy. And here I'm showing the ranging entropy of order Q. And depending on how you choose Q, you are choosing how to weigh the contribution of rare species versus common species, the diversity metric. So Q here is the parameter that's controlling how you weigh the propensity of these different species. So when Q equals 0, for example, all species are given equal weight. And so it would return, the Hill number would return a diversity of a diversity that's just the size of the support. That's not very informative. When Q equals 1, which is an interesting case, the Hill number returns a diversity that weighs the species according to their prevalence. So we'll see how we get back to this. Given this definition, we would try naturally to define diversity. Remember, we're given a collection of samples, a collection of observations, a data set. We would naturally define the diversity by trying to put a distribution over that collection of samples and then define diversity as the exponential of entropy, Shannon entropy, which is what we typically deal with in machine learning. So it's negative expectation under this distribution over the samples, log of the distribution. So this would be naturally something we would directly get out of this definition, exponential of entropy. But this is very limiting, even though that, you recover this form of entropy in a lot of areas in machine learning. In variational inference, this is how you define the entropy of the variational distribution, the distribution used to approximate the true posterior. In works that I have worked on trying to regularize GANs to be more diverse, use Shannon entropy as well. I actually did work on that. So you would define the entropy like this, and you're trying to find a way of approximating it. And in many other works, this is how we deal with entropy. This is not flexible because we have to define a distribution of a sample, which we don't want to do. And secondly, these entropies for models that are interesting enough is not tractable. You cannot compute it tractably. So how can we find a way of defining entropy that makes these things, that gives us these things that we want? So we looked at different forms of entropies and got to quantum statistical mechanics, which they define one broad entropy that you say is the von Neumann entropy. The von Neumann entropy of a, don't need to know quantum mechanical system or any of that, is just the trace of some matrix K times log K, where K is called a density matrix and it's used to describe the quantum system. So this was great for us because we're like, okay, this is using a matrix. It's not using a probability distribution. So maybe we are onto something. Let's try to see how we can leverage this to define a diversity matrix that's generated that doesn't have a reference or anything like that. If we look at K and think of K as a similarity matrix, use K as a similarity matrix, then it's density matrix, saying it, let's take the similarity matrix as playing the role of the density matrix, and using it as a way to describe the system, here the set of samples, then we actually get to what we want. We can define then diversity as the exponential of the von Neumann entropy. That would be something called von Neumann diversity. If we stick with the way ecologists call diversity, so it's VND. That's how the Vendi name came. It's von Neumann diversity. So we got to the Vendi score that way. It's defined formally like this. Let's assume you're given a collection of observations, x1, xn, and you assume that you are given a similarity function in the form of a kernel that we assume is positive semi-definite, such that the similarity between x and itself is 1, and the kernel matrix, the kernel similarity matrix that results from using this pairwise similarity function is Kij. So the I and j entry of the matrix is the similarity between xi and xj. And so you call lambda 1 up to lambda n the eigenvalues of the normalized matrix K. So it's just K divided by the number of elements in the collection. And the Vendi score is defined as the exponential of the von Neumann entropy, which you can easily show is the exponential of the Shannon entropy of the eigenvalue of K. And so we have extended von Neumann entropy to using similarity matrix outside of the quantum world. And we can use this Vendi score also as a new metric in ecology, because it doesn't exist in ecology, even though it was inspired by ideas from ecology. And it's also a Hill number, some of the things that they defined. And so we got something that we said, okay, this looks reasonable. Let's try to test it and see if it satisfies the properties we want. We extend it to the probability weighted version. This is in the case where all your samples aren't weighted the same, that there's a probability distribution over them. What just changes in the setup is that the matrix, similarity matrix now is defined by weighting it with the probability assigned to each of the observations. We want to deal with this case in the presentation, but this is an extension of it. So what you get is that it's exponential of entropy, it's a Hill number, it's interpretable, it's the effective number of dissimilar elements in the collection. So if two elements in the collection are different, so they have similarity 0, and the Vendi score is max. If all the elements in the collection are dissimilar, then the Vendi score is maximized and equal to n. You can get that by just plugging the similarity matrix will end up just being identity with identity, and you plug in exponential minus k over n log k, you will recover n. And if they're all the same, you would get a Vendi score that's equal to 1. And another thing that's nice here is that this number isn't changed if you duplicate certain elements of a category in the collection. Meaning if I have cats, dogs, elephants, and my similarity is just in terms of what type of animal I have, then if I add more cats or more dogs or more elephants, I still have 3 as a diversity metric. So this is what this is showing, those 2 properties, that as I add more different items, more categories into my collection, the Vendi score increases. And that even if I duplicate certain elements of the same category, it still remains that number. So it's illustrating those 2 properties. Another property that I didn't talk about before is that with the Vendi score, you can compose 2 different similarity notions of similarity. So for example, if you're a chemist and you want to capture both structural similarity and chemical structural diversity and chemical diversity, you can compose the 2 kernels and be able to capture that. Here we did this in a toy setting where we had one similarity that was solely focused on shape. So you see that here there are 3 shapes. The Vendi score will return 3. In the second case, there are 3 colors. So the Vendi score would return 3. In the third case, we are composing both color and shape. So it's reflected in the Vendi score, which has increased now from 3 to 4. This other metric called internal diversity is the metric that was being used in ML to measure diversity. It's defined as the internal diversity of the collection x1 up to xn is 1 minus 1 over n squared, sum ij of it's basically 1 minus the weighted average of the similarities of the sample. It turns out that that's actually not capturing some of these intuitive desiderata that we would want out of a diversity metric. For example, here, the internal diversity of this collection in this setup remains the same despite all these changes, despite the fact that it's normal that we get the same diversity here, because it's actually just changing from one similarity to the other. One was we had 3 different shapes, so diversity 3. The other one was 3 different colors, so diversity 3. But when you combine those, the internal diversity isn't able to reflect that because we're just averaging similarities. We will see all the failure mode of that diversity that's being used in so many settings. One of them being in doing generative modeling of molecules, where you actually do care really about capturing diversity well. It's being used there, and it's not capturing some of those things that we want. Another property is that if you have a collection of collections, the Vendi score of the aggregated collection only depends on the individual diversities of those collections and their propensity. So that's what this property is saying. It's just the geometric mean of the Vendi scores of these different collections. This was another simulation, just trying to understand that this metric is really doing something sensible. So we simulated a mixture of Gaussians, and we tried to control 3 different things that would affect intuitively the diversity of that probability distribution. So one was number of mixture components. As you grow the number of mixture components in your mixture of Gaussians, the diversity should grow. So this is being reflected in both the Vendi score and the internal diversity. The second thing you can control in terms of diversity for a mixture of Gaussian is the mixture proportions. As you make the mixture proportion more uniform, the diversity should grow, which is reflected in both the Vendi score and the internal diversity. A third thing you can control is the per component variance. So if you increase the per component variance of your mixture of Gaussians, the diversity should also increase. This was reflected in the Vendi score, but the internal diversity had the same diversity score for all those settings, which is also another failure mode that we wanted to illustrate. This is a trivial property, which is that if you permute the collection, the order of the collection, it doesn't change. Internal diversity also satisfies this, I believe. And there are more properties that we outlined in the paper that I recommend looking into. So, okay, now that we are comfortable with it capturing certain desirable features of property, and we're hoping that we will be using it, we need to look into the computation part of things. In terms of computation, there's time complexity and convergence rates. In terms of time complexity, it's O and Q. These are a lot because you need to compute similarity of pairwise similarity of the collection, but that's O of n squared. What's O of n cube is computing the eigenvalues. That's what takes O of n cube. In terms of evaluation, if you think you are in a reasonable setting where you don't have a gigantic collection, this is fine, which were our settings in the experiment. But if you are in a situation where you have millions and millions in your collection, it becomes unfeasible to do this. So there's that time requirement. One thing though is that if you define your similarity as a dot product, then you can dial it down to O of d squared n, where d is the dimension of your features. A lot of the experiments we tried, we were in that setting, but some of them we were not in a setting where we could define the similarity as a dot product. For example, n-gram similarity, which we use for some of the text experiments, we couldn't do that. So we would be in the O of n cube setting. The convergence rate is good. It's 1 over root n. You can read this in the paper as well, in the version 2 of the paper. We would update it there. So this is a good convergence rate, but time complexity. It's connected to determinant point processes. In machine learning, if you talk about diversity, this is something that people would automatically think about, because determinant point processes are stochastic processes that have been used to model diversity in different models, or for example, for subset selection. But it's different from Vendi Score in the sense that even though they're both parameterized by kernel, in DPP, you use the determinant of the similarity matrix as a way to define the likelihood of a sample of selecting a subset, whereas this is actually 0 when you add one duplicate. Or when you add duplicate, the Vendi score would still give you the same number, meaning it will, if it's the same, like we said before, if it's the same observation from one category that already exists, the diversity isn't changed naturally. For the DPP, it will return 0 as soon as you have a duplicate, which is not good. It's not something that we would want if we were to use it to measure diversity. So that's the difference. Another difference is in the interpretation part. For determinant point process, there's a geometric interpretation of it. It's a determinant, so you can think of it as a volume. Whereas for the Vendi score, we thought of it as an effective number, which is more directly interpretable than volume when it comes to diversity. The caveat in addition to the time complexity is that you cannot use it to measure quality of samples. That's naturally what it was not built for. It was built purely to measure diversity. And that's something to keep in mind, because if I give you a completely random set of image of this noise, would have a higher diversity than if actually, things that have the high quality. So this is not to be used to expect to measure sample quality. You would have to pair it with a metric of sample quality. If you're in computer vision, you can pair this with inception score. The inception score will give you quality. Perceptual quality tells you how good the image looks, whereas the vended score would tell you how diverse the samples you're giving are. Those are different things, but worth keeping in mind. Another thing is that it depends on the kernel. So if your kernel isn't sensitive, you wouldn't get good scores. If your kernel is way too sensitive, everything becomes picked up as a different sample. So you would also get meaningless scores. So it's really important to get the right kernel. If you are in a domain, your domain expert is something, people typically know how to measure similarity. For example, in chemistry, they have this thing called Tanimoto similarity that works on a lot of settings. So if you're in a domain where you have something like that, that actually is known to be sensitive to what it should be sensitive to, then you should be fine. But keep in mind that if the kernel isn't just sensitive as it should, then you may get unintuitive results. One thing to illustrate that here is looking at colored MNIST. Basically, you just color some of the digits of MNIST. Here, we try to reflect diversity in the coloring. So here, there's one color, so that's 5, 2 colors, that's the 6, and then 3 colors, and then 4 colors. So normally, if we have a kernel that works just fine, we would see an increased diversity as we move from 5, 6, 7 to 8, which is the case for that kernel. But for this kernel that use inception scores on these images, you get unintuitive results, meaning that here 5 is assigned more diversity than 6, for example, which is not the case. It's just to illustrate that, it's important to get the kernel behaving reasonably. So one solution that we're exploring is actually learning the kernel, so that so that we're hoping that the data itself informs the right similarity measure. We're looking into that right now. So I'll show a bunch of results in terms of applying this in different domains. For a lot of these, what we just chose was, for the images, it was inception score, inception embeddings. So there's this I3 big neural network that people use to get image embeddings. We just use those. They're from the I3 network, the big models. So we use that whenever we're dealing with images. For molecules, we use Tanimoto similarity. For the text ones, we use Ngram. So different kernel similarity depending on the domain you are in. Here, what I'm showing are results on molecular generative models. This is a setup where diversity is really key. So we want to have a metric that can inform us of the diversity of our generative model. There's a benchmark of molecular generative models. In that benchmark, there are different types of models. One was the HMM model. Another one was an adversarial autoencoder. And then in the third column there, I'm showing the actual real data set. What we're showing here is the kernel matrix of, we took 250 molecules and looked at the kernel, and you can see the duplicates in the colors. So the more yellow indicates that there are duplicates that are present. In the real data set, that tells us what we should be targeting. So you can see that this model, for example, this generative model, have way more duplicates than the real data set, but that the real data set has more duplicates than this adversarial autoencoder model. So we're trying to see if the diversity score picks up that. So the Vendi score is assigning lowest diversity to this one, as it should be. The next less diverse one is the real data set, as it should be. And then this model is assigned the biggest diversity, as it should be. For internal diversity, you get an unintuitive result, meaning that it assigns biggest diversity to this one that has duplicates. This is because you're averaging similarity. So it assigns biggest diversity to this, which should be the worst. And it's assigned the next best one is this one, fine, and then the real data set. So this was a domain where this score is being used and it's returning wrong results, and people didn't know about them. I think the difference is that we actually looked at a field, a scientific field that studies these things well, and actually, looked at their findings instead of just applying things out of the blue. So these are results on generative models of images. So we have generative models of images. We wanted to see how actually diverse are they, and also computing the diversity of the data sets for those generative models, because now we can do that. We don't need a reference, so we can just take any data set trained on which these generative models have been trained on, and get an actual ground truth on the diversity. So we did that for different families of models and different data sets. We use CIFAR10, ImageNet, Elson, CAT, Elson, Bedroom. These are benchmark data sets in Vision. So for each one, we have reported the Vendi score of the data set, using that as a target to see how diverse the generative models are. A result is that they're all less diverse than their original data set. These generative models are all less diverse than the original data set they were trained on, but that depending on the model family on the data set, some tend to be more diverse than others. There's no clear-cut definition as to which family of models is less diverse than the other. Although diffusion models tend to do well, if you look at IDDPM here, one row goes for both tables vertically. One thing where we wanted to evaluate the metric on is what's called mode collapse, which is a problem that generative adversarial networks run into. These are used in weather prediction, like DeepMind had this nowcasting paper where they were predicting the next 90 minutes of rain, and they use a GAN for that. GANs are known to collapse, meaning that they would just tend to return from the same mode instead of returning a diverse set of things. And the way people used to measure that failure mode is to use what's called number of modes, NOM. The number of modes, to find it, to compute it as a metric, you would have to run, you would have to pick labeled data. You have to label data, you fit a classifier on the training data, and you try to predict the classes of any new image that you give it as input, for example, images from the GAN, and it will try to predict the label for that image. And you count the number of modes as the number of unique labels predicted by the classifier. The hope is that the more modes, more different modes the classifier predicts, the more diverse the GAN is. The problem with that is that, first of all, you need to train a classifier when you're doing evaluation. Second one is that because you need to train a classifier, you need labeled data. Those are all limitations. And third of all, the classifier doesn't need to be good. It can just predict random labels, and you would say this GAN is diverse when it is not. So you also rely not only on a classifier, but a really good classifier. So those are three limitations, which means that if we could find a way of evaluating mode collapse without requiring to train a classifier, without requiring a labeled data set, then it would allow us to effectively, evaluate this failure mode so we can compare different GAN. And we are able to do that with the Vendi Score. That's why we tested it on this domain. It's telling us here that the number of modes for these two GANs that are supposed to not collapse, number of modes is saying they are both capturing all the modes. The total number of modes is 1,000 on this data set. The number of modes metric is telling us that these GANs are all covering all the modes. So we would conclude that they are diverse. But the Vendi Score is telling us that they're actually less diverse. Even though number of modes is 1,000 captures, they're actually less diverse than the original data set, which means that we have found something that's more sensitive to the nuances of the prediction. This is just another data set in Vision, where we were also doing some data set analysis, looking at what these data sets look like in terms of diversity. The reason why I found this one interesting is because Celebay is also an important benchmark in Vision, the important benchmark data set. And the Vendi Score told us that the labels in these data sets that are associated with men, you would find more diverse samples than the labels that are associated with women, which also, now we have indications that maybe there are biases in these data sets that we were not able to detect before, that we can detect now in an unsupervised way. And maybe we can, rework the data set so that it's less biased. Some people recently used the Vendi Score to do mode balancing in generative models. I found it insightful because I used to think only of these two. In terms of distribution and generative modeling, I used to think of mode collapse, meaning that we have this blue target distribution. That's the true data distribution. And you want to build a generative model that recovers the curve. So that would be mode coverage, would be our goal. But typically, generative models, even the state-of-the-art ones like diffusion models, they do miss some of these modes. GANs are the worst ones, but some of the other ones also miss these modes, some of these modes. That would be called mode collapse. This is one case of mode collapse. But actually, when it comes to diversity, and I got it only after reading this paper, was that we want mode balance. We don't actually want to, if you're doing generative modeling and you want to sample diverse sets, you actually want to sample all the potential modes with equal weight. So that if I have, let's say my data set is a data set of faces like Celebay, and there are people with darker complexions that you observe maybe just 3 people out of the 1 million observations, then if you build a generative model that would recover the curve, you don't have diversity. You still have the bias. Whereas if you do mode balancing, then it outweighs the observations in the data set that are less prevalent. So this was very, very insightful. And they found a way, they used the probability weighted Vendi score in order to do that for a set of samples. So let's go to another way of enforcing diversity, that was generative models, making them more diverse. But this one is a different domain. It's in the simulation, molecular simulation. How much time? Okay. So there's this thing called molecular simulation. The setting there is that we want to be able to estimate the physical quantities, some properties of molecules, and those properties relate to how a molecule transitions from one conformation to the next. And so what we do typically in order to evaluate those properties is run molecular dynamics simulation. But what happens is that here I'm showing one molecule that has two conformations. To switch from that conformation to this conformation, you have to jump through this huge energetic barrier, and that prevents them from jumping. Typically, they get stuck in one, so you won't be able to compute good properties. And so how do we leverage the Vendi score in order to jump this energetic barrier? That's what we will do. So to give a little bit more context, we are dealing with a molecular system, and the assumption is that the molecule is described as a set of atoms in 3D. So you call it X, and it's an entity that lives in R3N, and it's distributed at equilibrium as a Boltzmann distribution. The Boltzmann distribution is just proportional to the exponential of minus the energy multiplied by some temperature term controlling the temperature of the system. And so the goal will be to sample from this distribution, and you are hoping to get a diverse set of samples, so you get different conformations of the molecule. Typically, people use non-Jevons dynamics with replica sampling. So you sample multiple times, and you assume that those are independently drawn copies of the same molecule, and they follow this joint distribution. That is the product of the individual distribution. These individual distributions, they can all follow the same temperature, or sometimes you choose different temperatures so that you can, observe, you have a greater chance of observing different conformations. That's called parallel tempering. And what they do is just run molecular simulation, run Langevin dynamics. So what we will do here is, instead of just sampling them independently, we sample them from a coupled distribution, meaning that we would multiply this joint distribution with the Vendi score of the samples of the different replicas, and the energy that corresponds to this ensemble would be just the log of it, basically. So you would have the sum of the individual energy term, ui of xi. So those individual terms, but then you have the log Vendi score term, which is, remember, the eigenvalues of the similarity matrix induced by the samples. So that's the lambda I log lambda I. And then given this energy, each of the replicas, each of the sampled molecules follows, they evolve over time according to this stochastic differential equation. So dxi for the ith element in the collection, dxit over dt is negative gradient of the energy divided at xi. So this is a force basically term, gradient of energy. And then there's the gradient that's coming out of the Vendi term, we call it the Vendi force. You divide by some term gamma, and then you add the drift term, which is given by a Wiener process. So the Vendi force here is just the negative derivative of the log Vendi score. If you get rid of it, you would evolve these samples individually. If you add it, you're telling them, don't create this repulsion between the different configurations, right? Imagine a particle evolving over some space, some landscape. This second term, the Vendi force, is some repulsion force that basically forces them to not be identical. And that will allow us to also converge faster. So here, what you're seeing is a result of a simulation on some soil setting. This is called the Prince potential. It has 4 basins. Just basically think of it, if you probably, I used to think of it as just a probability distribution with 4 peaks. Physicists will think of it as an energy with 4 basins, equivalent to the same. You see the replica sampling method, which is what a lot of people use in molecular dynamics. It gets stuck. You cannot cross this other energy boundary in order to cover all the modes. Whereas if you're using the algorithm that we call Vendi sampling that adds that repulsion force, you actually do get, and it does that quickly. Quickly, it explores all these 4 modes. Whereas for replica sampling, for a number of steps going up to how much? More than, it's still not getting there. Yeah. Close to 3,000, 2,500, yes. And a long time, and it has still not covered all the modes. These are more results on real molecular systems. Alanine dipeptide, that's the baseline in biology that people study when they're looking at these sampling techniques. This is the ground truth we are trying to recover. This is a 2D map, 2D heat map of the different angles, torsion angles of this molecular system. So basically, this system just flips between 2 conformations depending on these angles, and this is the ground truth we're trying to recover, the free energy surface. And we got this by running the simulation for a very long time, because when you run Langevin dynamics for a very long time, it does converge. The problem is just that people don't have that long of a time, so they want something that runs faster, and that was the goal here. But this is ground truth. You can see that the Vendi sampler gets to that ground truth for t equals even 1 nanosecond. We already recover all the modes. Whereas for replica sampling, you have to wait until 10 nanoseconds to be able to start observing the final mode. Nanoseconds is a long time scale for these simulations, actually. So this is just the free energy, another observable that people usually are interested in, the free energy difference, because it tells you something about the system. And so here the idea would be that you recover the ground truth free energy difference over a reduced amount of time. And you get that with the Vendi sampler compared to the replica sampler. That takes longer to recover the ground truth, which is this dashed line. This is showing how it's doing that. This figure is showing that the Vendi sampler quickly managed to jump the energy barrier. So it's doing that transition, the number of transitions for the first few nanoseconds. You see how the Vendi sampler already has done a lot of the transition between the different configurations, whereas that's not the case for the replica sampler. When you extend now the amount of time, of course, the replica sampler will now start having these transitions, but by that time, the Vendi sampler has already converged. So that's what this figure is informing us of. This is a second system, real molecular system, that's called CLN025. It's a bit more challenging than alanine dipeptide, and we're observing the same gains in terms of convergence speed. So these 2 things that I discussed today, the references are these 2 papers. The first one is the Vendi Score diversity evaluation metric for machine learning that I worked on with an amazing CS student at Princeton, Dan Friedman. And the second one is Vendi sampling for molecular simulations, diversity as a force for faster convergence and better exploration that I worked on with 2 amazing students, Amey Pasarkar, Gianluca Bencomo, and a great collaborator of mine, Simon Olsen. And these are both under review. I would be excited to explore, beyond this, even how we can work on solving climate-related things. Thank you.
Great, thanks so much.
Thank you.
Any questions? Maybe starting with early career scientists in the room. That's the mic. And maybe if someone, I don't know if you're like monitoring just the message online.
Thank you for the great presentation.
Thank you.
So I was wondering what the implication of having a metric that's measurable, like the Vendi score,
Yeah.
is in terms of training large machine learning models.
Yes.
So does it help us during the data selection phase, like downsampling or sampling, or can we integrate such a score into the loss function such that we don't have to sort of do that? You know, I mean, I'm trying to sort of stress this to like active learning sort of selection data, but then can we just integrate it to the loss function somehow such that we don't need to, like, human selection is always going to be biased.
Yes.
Score is, you know what I mean?
Yeah.
So yeah, that's my question.
Yes. We're working on those things. We are leveraging it right now on many projects. But what you said is that one thing that it seems and these are very different domains. For example, if you have low result, if you are in a low result setting and you wanna train your model and get good enough performance, typically what people do is they're looking at this thing called dataset distillation. You wanna get a smaller version of your data set, and you want to be able to train a model, say a classifier, and get a performance that's reasonable compared to if you train on the whole data set. Of course, training on the whole data set will always yield better performance, but you're hoping that you've selected the subset of the data such that you get a reasonable performance compared to if you train to the full model. So that's an important setup for low resource setting. You can imagine using the Vendi score to do that selection so that you get, a diverse, small enough sample that you're hoping that captures the essence of the full data set and achieve that. So that's one, like, training larger, the data set part. But then in terms of model algorithms, it's everywhere here. Yeah. Monte Carlo, active search, generative modeling, all of these are very relevant in a lot of machine learning related. Machine learning for science. The Vendi sampling actually isn't machine learning at all. It's chemistry, chemical physics, because there's no data in there. It's just simulation. Yeah. So it's just to say that it's general. Yeah.
Any other questions?
Yeah.
That's great.
I was curious about some of the examples you showed, whether it was both shape and color and things like that.
Yeah.
I'm curious how you can weight which one is maybe more important to the diversity score, I see.
This one. This one.
Yeah, that's kind of what I'm
Yeah, so here what we did was just say if it's the same shape, for here, if it's the same shape, K is 1, otherwise it's 0. So wherever you see yellow is 1, otherwise it's dark, black 0. For here, if it's the same color, is 1. If it's not the same, if it's a different color, is 0. For there, we said 1/2, if it's one or the other, that's where you're seeing red, that's 1/2. Yellow, if they're the same shape and the same color, and 0 otherwise. So I guess depending on how you define the kernel, you can enforce that. You can enforce what you weigh or what you don't. That's where the domain knowledge comes in. It's a double-edged sword in that you do want to let the user have a say in terms of what diversity they want to capture. So whether they care more about structural diversity or chemical diversity, vice versa. If they care more about the color of the images or the actual content of the image, the user has a say on that. But the bad side of that is that you are asking the user for that. So some users may want to specify that, others may be like, I don't care, I just want to get something. So that's the kernel part. It's the thing that still bothers me a little bit. I think learning it will lift that off.
Yeah, I think that's interesting. And I mean, just because you have the suits and ranks or whatever, but the card symbols on there, you could almost think of an end-to-end setting where you could say you could perhaps weight the diversity score based on how likely you are to win a hand in poker or something like this. Where in that case, I think you'd actually want a least diverse hand.
Yes.
More kind will win more games.
Yes. Yeah. Yeah. Or maybe some mix of the two where you get input, but also combine it with the learned part. I'm not sure. And compose the two. Who knows? Yeah.
Any other questions? No? I ask a question.
Yes.
I was wondering, very interesting talk, by the way.
Thank you.
I was wondering, like, what if you have like a really fat tail, like very extreme events, and then
Yes.
you're sampling, let's say, I'm thinking just like, for instance, temperature historical, and you might be very undersampling, especially the tail of the distribution.
Yes.
Would that affect your metric and your diversity metric?
So the Vendi score is, remember the beginning when I mentioned hill numbers? Where was this? Where was I? Here. Yes. So if you want to give more weight to rare samples, so you're in a domain where rare events are really important, you would pick a different version of the Vendi score. That's not Q equals 1. Q equals 1 is the Vendi score, would correspond to a Vendi score with like the similarity matrix thing, that construct. But you would have to pick a Q that's less than 1 in order to, give more importance to rare items. If you want to give more importance to common items, you would pick Q equals infinity, which is just one over maximum of the eigenvalues. Yeah, the Q equals 1 is a nice trade-off between those two extremes. Yeah.
Great. Thanks so much.
No other thanks questions. So let's thank again our speaker. Thanks so much.
Thank you. Thanks.